So the other day, I had a random thought on how I could potentially make a better pathfinding algorithm for MIT Battlecode. It ended up not really working. I think there are some cases where it could be interesting, but I think for most MIT Battlecode maps, it doesn't quite make sense. But to back up, first I'm going to talk about MIT Battlecode. If you've never heard of it, then I'm going to talk about some of the existing pathfinding algorithms people use, and then I'm going to talk about this new idea, which I'm calling either grid search or quad search. It's probably not new. And then I'll talk about a technique that I later figured out that I think I actually will use, but I think other people already use it, but I'm not 100% sure. But anyways, if you've ever heard of MIT Battlecode, it's very cool. It's a programming competition hosted by MIT. They give you a game spec and a Java client, and I think Python's going to be introduced this year. And basically just program these little bots to play a game for you, and it's fun. There's a leaderboard. It updates all the time because you have to submit your code. There's usually like resources, bases, units. There's also fog of war, so you don't have perfect information about the board state. And as a fun constraint, you only get to execute so many things. So they track bytecode, Java virtual machine bytecode. You get about 10,000 instructions, which is like, it's not exactly, but you can think of it as like 10,000 assembly instructions or kind of like 10,000 operations you're allowed to do. But things like calling functions and stuff take up a certain amount of bytecode, like 5 or 7 or something like that. And so you have to be kind of careful about what algorithms you run. And so one of the big things you have to do as part of MIT Battlecode is pathfinding. So we can imagine we're at green and we want to go to red. Somehow we have to get over there. Now, if we had unlimited bytecode, we could do something like A star or Dijkstra or breadth first search and always find the perfect path. But since we have that bytecode limitation, we can't do that. And so instead we have to be a little bit more clever. Now and so this is a breadth first search. You can see, you're just kind of starting from your starting node. You look at all the neighbors, then you look at those neighbors, you look at those neighbors, and you keep going recursively, or I usually use the queue until you can get to that final node. But like I said, it's too expensive to actually do this. And so the idea is kind of based off of this, but I'll come back to that in a second. So instead, an algorithm a lot of people use, and MIT gives lectures while this competition is going on, and they talk a lot about the bug nav. I think there's 2 of them, but there's only one actually useful one. And so with bug nav, instead, what you're going to do is you're just going to move towards the target until you hit an obstacle. This black thing is a wall. Once you hit the wall, you're going to follow the wall. You can either go right or left. And so you just keep the wall on either your right side or your left side, and you iterate around until you get to the other side of the wall. And then from there, you leave the wall and you continue. There is some fun stuff with bug nav. Bug nav can kind of run into some awkward situations. For example, here we have another bug nav. We're at green and we want to go to red. So we can imagine we're going towards red. Eventually we hit a wall. So we're going to go around the wall. We're on the other side of the wall. We continue. We hit a wall. Now we're going to follow the wall and the wall goes all the way back and then around, and then you get to red. So bug nav usually is pretty good, but you can definitely create cases where it just does not work well at all. Anyways, bug nav, very popular. It's also very simple. It's very local. You can kind of see where you're going. So definitely an algorithm that a lot of people use. I think another algorithm people use, actually, before I talk about that one, the one I sometimes use is, I don't know what it's really called. I call it like DFS with a priority queue. But basically, instead of doing like breadth first search, instead of like evaluating all these nodes and then evaluating these nodes, you can do kind of a depth first search with a priority queue. And so you're going to be evaluating the node that is closest to the target. So for this one, I didn't implement it, but for this little demo thing, this is in JavaScript, not Java, so I didn't copy any of my old code. But you can imagine like you would search this node and then this node and then this node, and this node doesn't work, so you'd search these 2 nodes, then these nodes, then these nodes, and eventually you'd hit a node that can kind of sneak around, and then it would be this node, this node, this node, this node, and then whatever node is closest. That's usually what I end up doing. That, and also you have to do pathfinding. You have to do a lot of micro, because pathfinding isn't everything. Like on the way, last year there was like this paint system where like you would only want to step on certain tiles. So you might path somewhere, but then while you're pathing there, you might find out that like it's better to kind of like step diagonally in some cases because you want to stay on a specific paint tile, or maybe you're trying to go somewhere, but like there's like an enemy approaching, so you kind of veer out of its way. Or like a couple of years ago, there was like a capture the flag sort of thing where like people would be grabbing something and running back, and you want to make sure there's no congestion, that thing that has like this goal thing, they get all the priority they want, and so you kind of get out of their way. So on top of these like kind of goal-based pathfinding, you also have just a lot of micro code. And so sometimes you don't really always follow this code. But anyways, and then the last one is the one I don't know much about, but there's I think a bunch of people use some Bellman forward code that was like specifically written and bytecode optimized. I've looked up, I've read some resources and I hear other people describe it. I kind of understand how it works. It's doing some like convolution with bitmaps, and somehow from there you can kind of relax and find an optimal node. Or an optimal path. To be honest, though, I don't really understand it. I feel like I just understand the words, but not how it puts together. So I think maybe after this, if I have time, I'll look more into that algorithm. But unfortunately, I think a lot of people just kind of copy code, which, I mean, that's part of the game. Kind of on a tangent here, but I kind of hope in future years of Battlecode, they like change up the game type. So instead of doing like a 2D grid, they go to like a card-based game or Pokemon or I don't know, something else, just so that people don't copy as much code, because I feel like it kind of takes away. Like if you read a number of the write-ups for last year, you can see like it's just like a bunch of, you copy such and such team's microcode, and then you copy some other team's pathing code, and then like some resource utilization code. And so the code that is winning is just like code that's just like copied from other people, which is not bad. I wish there was more creativity. So it'd be fun if there's like a different game style where you can't copy code like that. But anyways, I think a lot of people use the unrolled Bellman forward code. Cool. So anyways, so I want to talk about this new idea that I had. And so the idea is this region right here, this 4x4 grid, is like super boring. Like there's no reason we should ever search this code, or search this when using like BFS, let's say. Like there's just nothing there. And when we're also BFSing through like a region like this, a big empty space, like why are we evaluating every single node? Like there's nothing special about this. Like just a move towards algorithm works perfectly well. And so I was wondering, what if we were to kind of discretize or grid or like simplify the map so that instead of representing this as like 16 elements, we just represent it as one element. Because there's nothing special about this. It's one element. You can't go up, you can't go right, but this one element can go left or down. And so if we can kind of like figure out the right way to grid up these structures, then we can BFS or DFS on top of that, and hopefully go much faster. Because if we were able to grid this, and I'll just jump ahead and show it. If we were able to grid this, again, this is the walls, this is the start, this is the end. Each of the grids just has its own unique color, and there's just a grid ID, which is just a random number. You can ignore the numbers. So we can see we have a 4x4 grid here, we have a grid here, 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 blah, 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 here. Now, if we were to BFS on top of this, it should be much quicker because we have one node that can go to two nodes, or a couple nodes, but I technically don't do diagonals for a reason. So this node can only connect to two nodes. This node is only connected to 1, 2, 3 nodes. This node is only connected to two nodes. Like it is very fast to BFS once you have this structure. So the hard part is kind of creating this structure, correctly splitting up the grid. And technically it should also involve fog of war, which so you only have some sort of visibility radius, which I'm not going to tackle that right now, but instead we need to figure out if there's an effective way to create this grid-like structure and what this grid even looks like. I obviously already calculated it and already have it, but where do you actually like divide and split up your grid? So I guess answering that question first, like how should you, like what is an appropriate unit to split on? And kind of the definition I ended up using was the border must be completely shared with a region you can move into. So like this whole region, let me look at a different map. Maybe a gulp. Yeah. So we'll look at this. So the kind of darker structure are walls. We have a start and an end. Yeah. And so this is all, it's kind of, two walls that are kind of like gulping in. So you could think that this entire structure could be one zone because it is very simple, but I don't know if that will always work. I think it's better if a zone fully shares a side with a different zone. So like if this whole area was a zone, you have this like weird element here. And so can you always move towards it? Like can you always just easily pass through it? And I don't think so. I think there might be some weird cases where you don't want that. And it's also just kind of hard to define, like, is this a simple structure? Like, because the Battlecode maps can get kind of nasty. And so instead, I think it must be continuous and, like I said, share a side completely. And so instead of having one big zone just in here, we have 3 zones. So we have this 2 by whatever that is, 8 or something like that, 1 by 8, another 2 by 8. And I think that works out kind of well. Maybe you could optimize it more. I'm not too sure. Next question is like, how do you actually generate these? And I realized that I think the best way is just to look for corners. So like a corner here, once you have a corner, you kind of split off from this corner and cut it and create zones like that. And so it can either be outy corners or any corners too. It should also be split. There's a data structure and I guess algorithm related to this called a quad tree. It's used by databases for doing geospatial indexing, and it's kind of what we need. I thought at first it was exactly what we needed. It doesn't quite work, but it gets us most of the way there. So a quad tree, it's a very simple data structure. It's just a tree, and the tree either has 0 nodes or 0 children or 4 children. And the idea is we could say that this whole map is a node, and at some point we want to split it, and we split it into 4 different children. So let's say we split it like right here on this corner. The top left would be a new node. The top right would be a new node. Bottom left and bottom right would both be new nodes. And so we split it into 4 different chunks. And so now you can ask the tree like what group is, some location in. It would see like, it would look at that split location and say, am I to the top left of that split location, to the top right, to the bottom left or the bottom right? And it can kind of go down like that. And so I think this data structure is interesting because you can kind of get like arbitrary like resolution or block size in some areas and kind of ignoring other areas if like that area doesn't have as much detail. So if you just have like a big open region, you don't really need to like split there too much. You just kind of like leave it as a big open area. But if you have like an area with like a lot of walls and details, then you can kind of like zoom in using this quad tree structure to get like really deep and very granular. So pretty cool data structure. There's a couple of issues though with applying quad tree to this kind of grid-like search. The first is quad tree is very localized in that you only care about what's happening in your little area, whereas with this, sometimes you're split. Like if you split, like let's say you split maybe here, and you haven't done this split yet. Let's say this is the very first split you do. If this is the very first split you do, you're going to have a region there, 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 and there. And then let's say later you do a split here. This is splitting only within this zone, but you need to split this zone and this big zone over here because you need to have this split go all the way across. And so because of that, you don't quite get the tree benefits of the quad tree because you have to go up and out. And when the maps get more complex, like this is a pyramid sort of structure, like there's a lot of splitting and you just don't get much benefit. And like I said, you also need to split across every zone. It is very possible that this zone and this zone are like very far away from each other in the tree. And this tree probably has a very unique structure that might not be as flat as we want. It could be like very deep for all we know. So it's not quite a quad tree, but we can kind of think of it as like a quad tree. And like I said, the difference is when we split, instead of just splitting within our zone, we have to go follow this line all the way through and see what other zones it's hitting, and then split in those zones too. So there's going to be lots of splitting. So hopefully that made sense. But anyways, if you do that, you will get a split like this, and it kind of works. So once we have our zones, we'll just BFS on top of each of these zones. So from this zone, we eventually want to get to this zone. So we're just going to see what my neighbors are here. It's this one and this one, and then from here, this one and this one, and then from there, this one and this one, this one, this one, and this one and this one. And it kind of works. You might realize that BFS is interesting, but it's not quite what we want, but I think it's the best of what we can get because this doesn't have a link weight of 1. It has a link weight of potentially 4, but it could also be 1 because like if you're just cutting through this corner, it has a link weight of 1. But if you're going all the way across, it should have a weight of 4. But you don't actually know what the weight is. Like I think you could kind of guess, like maybe you could do a line through, but then that gets kind of expensive for calculating the weights, and it's going to depend on like all the different angles you're going through because you don't technically know what angle ahead of time you're going to try to go through. So kind of nasty, but there's a somewhat of a solution to that I figured out later, which we'll talk about in a second. Let's see. And I think I will talk about it now. So one issue is, let's go to gulps, maybe gulps 2. Good enough. So we have to connect all the nodes. And it does some silly stuff sometimes. So we're connecting this node to this node to this node to this node to this node, this node, this node, this node, and this node. You can probably see. And when I connect a node, like I don't know where in the node I want to route through. And so we need a way to kind of like smooth it out, because right now I just go to the middle of a zone. And so if there was some sort of algorithm to smooth things out, that'd be super useful. And it turns out this algorithm, if we had such an algorithm, would also be very useful for bugging. So for example, when I bug here, like it's kind of silly that we go all the way to this wall just to go back out and around, and then like also we go down and then to go back up. We kind of want to smooth it out a little bit. And like we can see like there's an optimization, a trivial optimization we can make here. Like we go all the way down and around. Like why go here to here when we could just go from here to here? So I'm calling this like relaxing, this new algorithm. And what it does is, so it'll go through this path that we calculate, and it will check to see if going from 1 to 3, so from 1 to 3, or so 2 ahead, is it connected? And if it's connected, we can just splice out that one node. The other thing we can do is we can see if the move towards from 1 to 3, if it's just a little bit closer. So like there's no reason to go here to here when we could just go here, here, here. If we go here, this node is closer to this node than this node, so we can get rid of this node. It doesn't actually make a difference step, but doing that optimization step sometimes allows further optimizations in the future. So it's best to always get the closest node. And so if we were to optimize this one, I wish it would be better on pencil and paper or something, but you can see we're gonna go here, so then we're gonna go this one, and then instead of going boop, 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 we can go boop, boop, boop. And then once we have that one, we'll go boop, boop, boop. And then eventually it'll relax all the way out, and we're just going to go straight across. And to see what that actually looks like, I mean, we don't get to see the actual implementation, but we can see eventually we get relaxed all the way out to here, and to here. And this is using bug. And so this also works for grid. This was what grid was without the relaxing. So that looks pretty good. We go to here, we go to here. We have this extra step here, which we really don't need. And we could cut across here to potentially save one. Yeah, that'll save one. So we have two different optimizations. So we optimize this corner, and we optimize that kind of weird back and forth logic right there. So this works pretty well. And I think grid, this like relaxing, like I said, we're going to go through the chain. We're going to look 2 ahead. We're going to see if we can either directly go to that 2 ahead, or if we can make it just a little bit closer, and then try again to see if there's like a node we can skip to go ahead. And during that, you also have to check and make sure that you're not stepping on a wall, obviously. Like it would be closer if this could step here and then here, but there's a wall there, so we can't relax there, obviously. So pretty cool. The relaxing code actually worked pretty well. So I do like that. I don't know what the bytecode of it is, but I think relaxing is like an optimization you can kind of do like after the fact. Like you can relax as much as you want. So you could like just do it like you generate a path one turn and you see you don't have any more bytecode, and you're like, fine, I'll just take a step. And then next time, now that you already have a path that you're on, you can then start relaxing it with any spare bytecode cycles you have, just to kind of smooth out the path and make it more efficient. So I think overall, I think the grid structure is interesting, but I think there's just like so many. I think in the real world, if we had a map that was much bigger and much more open, I think grid would be very cool and probably efficient. But I think currently the maps that we've been playing with historically have been decently big, but they can have just a lot of structure and a lot of corners, in which case I just don't think it's worth the upfront investment of constantly building this like grid-like structure. And the grid's kind of complex to actually implement. Like differences between nodes and corners and splitting the corners all the way up was a little bit tricky logic. It wasn't terrible, but it's just kind of complex code that, if you can avoid the complexity, that's probably best. So I think for me anyways, I think this bug relax algorithm is actually pretty cool. So I think I'll probably actually just stick with this. This is like one that bug should be discussing on. Yeah. So like it's going to go all the way through, realize that it can't. It's going to exit that little gulp and then come out. And then it's going to try to follow it, because it's doing the wall follow, it'll go there, which it really shouldn't. It really should just connect across, and we can see the bug relax does that. So I'll probably stick with bug relax. I think it's good. But anyways, thanks for watching. If you have any ideas on how to make this better or any improvements, I'd love to hear it. Otherwise, I'll see you next time. Cheers.